So now we're at the point where we can use everything from the semester or everything from this class to really just look at some data, choose a model, and see what is the best way forward. So that's exactly what we're going to do. Don't forget that making inferences, it means you have a sample and you're using that sample and analyzing it in order to make implications about the whole population or inferences about the whole population. Okay, so there's always going to be some error. So we're going to also talk about the limitations, because if you're going to use a sample, then you haven't really used everyone or everything within that population. However, that seems pretty tough to do, to be all inclusive all the time. So we use samples a lot and say it's probably what's going to fit for most people. And we just hope that that sample represents us in some way or reality. Now, this is actually not in your book, but I feel like it should be. Arrogantly, I feel like it should be part of your book. And because it draws all of these ideas from chapter 4 together. So we're going to go ahead, we're going to look at data. So I called this section 4.11 because that was the end of the book, but really I feel like let's just toss them all together and see what we do. Okay, example 1, the stats come from the Bureau of Labor Statistics because honestly, we hope that our politicians are making data-driven decisions and also people-led decisions for the people, by the people, for the people. So what you see is annual spending. Okay, let's see. So you have an age group under 25. That's represented by the age of 20, and with an average annual spending of about $24,300. Then you jump to, here's the biggest spenders, the age group between 45 and 54, and the representing age for that is, if you're in this age group, you're about 50, or you're about 49 and a half, and they spend on average $48,700 per year. Now, most of these people have people depending on them. And so they spend their money on, say, kids or whatever, houses, cars, food, for not just themselves, but for other people too. So, and then you see with this older age group, their spending goes down to $32,200 on average. Okay, so let's start this. Let's create a scatter plot and label everything. Put it next to the table. Okay, so I went ahead and I made some decisions. My first decision was to say that this is the explanatory variable and that spending depends on your age, or spending responds to how old you are. So I went ahead and called this my explanatory, put it in L1, and I called this my response variable and put it in L2. And so let's go ahead. So take a moment and put those into the lists. Remember, that is stat, edit, and then you put in all of your data. Okay, so here comes the calculator. Whee. I'm gonna have to maybe go side by side here. Okay, my decisions are that this is age and this is spending in thousands of dollars. Okay. And I want you to notice, so stat edit, that in list 1, I've put the age representations for each grouping. And in list 2, I put the corresponding, matching up pairwise, spending for each age. So here we see that 50-year-old spending $48,700. Okay, I'm going to go to, first I'm going to go to y equals and clear out anything. Then I'm going to go to my stat plot, and make sure everything's on the up and up. Turn it on, it's scatter plot, but oops, this should be L1 and list 2 for age along the X's and spending along the Y's, and then I go zoom 9. And here's our image. Look at that. Look at that spending curve. Okay, so let's go ahead and make a rough sketch of that. So I see this is for the young people, the U's. And okay, way up here, there's a pretty big jump, a not so significant jump. Then it comes back down and ends about there. Okay, rough sketch of what I saw on my calculator screen. Okay, and create a model equation for this data. Well, I look at this scatter plot and I think to myself, okay, there are 4 models, and I'm going to go ahead and jot them down. Let's see. Could be linear, could be quadratic, could be exponential, and could be inverse variation. All right, immediately it has curvature, so linear is out. Curve. There, I'll turn that into my U, even though it started as the C. Curving, whatever. So linear is gone. I don't see that it has any boundaries. It's doing an increasing then decreasing. So immediately I'm drawn to the quadratic model. No asymptotes. Yeah? And that's how I ruled these out. Okay, so create a model equation for this data. So we had to make some decisions. We had to look at our 4 data models and then say which one and why we chose that. Good to go. Increasing then decreasing, maybe. So maybe show that there's a rebound here. Yeah? Okay, and now it's time to use our calculator again. So back to the calculator. Stat, calc, quadratic. So we have chosen to use the quadratic and we calculate. All right, let's copy this down. It's a pretty good match, by the way. It's an A in terms of data fit. Right, so we went stat, calc, quadrag. Let's write it down. Our spending, so I'm going to call it S for spending. S is approximately negative 0.0348 times the age squared. I'm going to call it A for age, plus 3.2544 times the age. And remember, I'm using 4 decimal places as specified, minus 26.3423. Okay, so here's our model. I said S equals spending in, oopsie, thousands, I can spell. And A equals age of the spender. Graph your model equation with your scatter plot. Okay, back to this guy. Whee! Okay, and so now we go to y equals, and we put in our equation. Uh-oh, I need to slide it over so that I can see my equation. Got it, negative 0.0348 x squared plus 3.2544 x's minus 26.3423. Okay, and we graph. Wow, that's pretty good. That is such a really good model. Okay, So at least visually speaking, I feel very comfortable that we've made good decisions. So let's go ahead and make a rough sketch of that on here. It actually hits each one. It goes a little bit under this one and a little bit over the peak one, but it travels pretty much straight through all the rest. So it went like this. Rough sketch. Wow, pretty good, pretty good, pretty good. Use your model. Okay, so that means equation. Okay, to find the annual expenditures of an 18-year-old person living in the United States. Okay. Then show how much error the model had from the actual amount. Okay, so an 18-year-old, that would be A. So A equals 18. Spending is approximately negative 0.0348 times 18 squared plus 3.2544 times 18 minus 26.3423. Okay, that is a calculator business for sure. So negative 0.0348 times 18 squared. So far so good. Plus 3.2544 times 18 minus 26.3423. Got it. I got about 20 point, I don't know how much we're supposed to round to. I'll go with 20.96. I don't like rounding to more precision than what we were given in the data table, so I'm going to actually round that. This would round up to 10, making this, well, 10 tenths is 1. Okay. Got it. So now that's certainly not a 20-year-old, and I think 20-year-olds actually spend more than 18-year-olds, but the data said that that age group spends on average $24,300. So how much error did the model have? Well, so this would be right. And so it looks like this is an underestimate by what? $3,300. So I'm going to write that down. Model underestimated by $3,300. Okay, but that doesn't, I mean, that's actually perfectly okay in my mind, because an 18-year-old, that's a big bucket of people, all people under 25, and this is their average. So the fact that an 18-year-old had a little bit lower by this model's prediction, yeah, that's all right to me. It's not necessarily a flaw in the model, actually. Use your model to find the age of people living in the United States with an average annual expenditure of $45,000. Ooh. Okay, here we go. So now all of a sudden, remember this is in thousands of dollars, we are given that S equals 45. So if we look back to our model, here's our model right here, we are saying 45 is equal to negative 0.0348a squared plus 3.2544a minus 26.3423. We subtract 45 from both sides. So remember, set equal to 0. And 2, find the A, the B, the C. And 3, go to town with the formula. So subtract 45 from both sides. What's 45 more than 26? 71. Okay, so far so good. Now, here's the A, the B, and the C. Gonna go like this. I don't care. If you want to include this plus, that's fine. It's positive. These two are negative. This one is positive. Okay? And we go ahead and we move forward with our quadratic equation. Whew. Here we go. A is approximately the opposite of B, so negative 3.2544 plus or minus. And now I'm actually going to go ahead and do the whole square root on my calculator because it's huge with all of these decimals. So square root of the quantity, so parentheses 3.2544, that parentheses squared, and then minus 4 times, and this is all under the radical still, 4 times A, negative 0.0348 times, so 4 times A times C times negative, and make sure when you're putting in these negatives, so I'm going to show my calculator really quick, that you use the negative sign. So here's the subtraction sign, but make sure that you're using this negative, otherwise it's going to think that you're not multiplying anymore. So make sure when you're inputting these negative 71 business that you're using that negative sign. Okay, so let's see. Negative 71.3423. Okay, so for that radical, I ended up with approximately 0.8126. And this is all divided by double the A. So negative 0.0348 doubled is negative 0.0696. And then we have the either or. Okay, so either, we're going to add, then divide. So either A is approximately, here I go with the addition, negative 3.2544 plus 0.8126, that quantity divided by negative 0.0696. Age is approximately 35.1, or age is approximately, now I'm going to go with the subtraction, yes? So negative 3.2544 minus 0.8126. Take that quantity, which was negative 4.067, and divide it by negative 0.0696, and I get approximately 58.4 years old. Okay, so use your model to find the age of Americans with an average annual expenditure of 45 grand. And I ended up with either 35 years old or 58 years old. So let's look back at this table. A 35-year-old would be somewhere around here. And that makes sense, about 45 grand in between there. And then a 58-year-old would be somewhere here, closer to 59. And so that makes sense because, again, that's 45 grand. Okay, so just so that we remember that the quadratic model goes with the quadratic formula, and we had steps in order to find that, and that we actually had an answer with two different ages. So find the age of people in the U.S. with the average expenditure of 45 grand. About that. Okay, so we had two answers here based on the quadratic equation. And then before I move on to the next example, I also wanted to show you that is visualized by if we put in here a Y2 of 45 grand. and we put that on the graph, there are the two ages where they intersect. So here is about 35 years old, and here is about 58 years old. Okay, nice. So let's do it with a totally different data set in example 2.